Good morning, respected faculty members. Am I audible?
Yes, sir.
Yeah, good morning, respected faculty members. I'm Rajesh, Department of Civil Engineering from Kallam Harnath Reddy Institute of Technology. Let me introduce our today's speaker, Dr. Subbarao Pichuka. He is working as an assistant professor in the Department of Civil Engineering. He has been working on some exciting as well as useful problems in the research area of nature of changes in various hydroclimatic variables over the Indian landmass in the wake of changing climate during the 21st century. And he has been working in IIT Madras. Let me hand over the session to Dr. Subbarao Pichuka. Thank you.
Yeah. Hello. Yeah. Thank you so much for a brief introduction of mine. So, Rajesh, right? So, yeah.
Yeah, sir. Yeah.
Yeah. Thank you so much, and I welcome all the participants to this online FDP. Uh, so, shall I share my screen?
Yes, sir. You can share, sir.
Yes. Okay. To share entire screen. So, can you see this?
Sir, you can share the screen, sir.
Yeah, I shared my entire screen. Sorry, what did you say?
Yeah, sir. You can go with the presenter mode, sir.
Presenter mode. So, is it visible?
Yeah, sir. Okay, sir. You can continue,
Yeah.
sir.
Can you also please confirm whether the slides are changing?
Yeah, sir. It's changing.
Yeah. Thank you so much for the confirmation, Rajesh. So, I welcome all of you to this, faculty development program being held at KHIT Guntur. So the topic where on which I am going to talk is downscaling techniques and their ability in managing water resources under climate change. So my areas of interest, which include hydrological extremes, climate change impacts on water resources, integrated watershed management, and urban hydrology, etc. So I know participants are from different, background in especially civil engineering. So at any moment, if you feel you have something to clarify, so you can just unmute your mic and you can say. So with this note, I would like to continue this talk. This is outline of this presentation. First, we will see the introduction to water resources, or especially surface water resources. Then we will see why the downscaling techniques are required and what is downscaling, etc. Then we will see about some very recent downscaling methodologies. Then I will discuss about the applications of downscaling techniques, followed by the future scope, then references. Well, this particular talk contains several, technical terms. So for your convenience, I have put some of the things which I am going to use in this talk are here. For instance, GCM stands for General Circulation Model or Global Climate Model. TVDM stands for Time Varying Downscaling Model. CORDEX is Coordinated Regional Downscaling Experiment, and RCP is Representative Concentration Pathway. So these people who are working in the field of climate related studies and all are quite aware of these terminologies. Of course, for others also not an issue if you aware of or not aware of. So I try to make more generalized my topic and try to present some of the insights of the research which I have been carried out so far. Well, let us just talk from broader sense. So let us understand the things from broader sense to just confine to a particular talk. So if we are talking about basically the climate change has rigorous impacts on several sectors like industrial sector, agriculture sector, the economy of country can avert, and it has great impact on several other features are like water availability and agriculture change, etc. So, but overall, all these things are basically covered by a big natural cycle called hydrologic cycle. So of course, I mean, everybody know that what is hydrologic cycle. So some water will evaporate from oceans, then it will transport, then it will condense in the air, then it will precipitate. So then finally some part of water will go in as infiltration, some part will go as surface runoff, etc., etc. So all these things are very much clear to us, but let us see where exactly the definition of hydrological cycle starts. So, for example, there were some things related to this hydrologic cycle in our scriptures like Bhagavad Gita or something like. For there is one sloka stating that Akashat.
అదే సార్ 95 అట్లా అవ్వగానే పెట్టేద్దాం.
Hello. Yeah. So there is something called Akashat Patitam Toyam Yata Sagaram Pratigachati. So the water which is fallen from the sky will go eventually into the sea, then the cycle will continue. So that is what the simple hydrologic cycle is. And most importantly, majority of population are relying on the surface water resources. The surface water resource something which is basically there on the surface of the earth. It may be lakes, or it may be rivers, or it may be some atmosphere water,
ఇంకా ఆయన
or
కదా సార్ host.
uh, hello, somebody. Hello, are you talking to me? Yeah,
సార్
yeah, fine. So that is what there. So whatever which is there on the surface of the earth or above the surface of the earth, we are basically treating it as surface water, which includes uh, any body of water found on the earth's surface, including both the salt water in the ocean and the fresh water in rivers, streams, and lakes, etc. A body of surface water can persist all year long or for only part of the year. So that may be perennial river or ephemeral river or whatsoever it is there. So basically, what happens? There is some kind of inter exchange between the water which is there on the surface of the earth and which is there on the below the surface of the earth. So that is groundwater basically. So some part of surface water will contribute to the groundwater through the process called infiltration, deep percolation, etc. Thereby, some groundwater part of groundwater eventually come and meet the surface water through the process called springs and natural movement of groundwater, where the a slope of river is coming down and which meets the groundwater level in that region. So there eventually the groundwater will come onto the surface water and meet with that. So these exchanges are also there, and which are very complex in nature. And to be specific, all of us know that water is the most precious resource on our planet. But still, if we look into the entire planet, almost three-fourths of our planet is covered with water, and only one-fourth of planet is covered with the land resource. In that case, basically the land is the precious resource. Then why we are calling water is the precious resource? We can get the answer from this slide that majority of water resources which are available to us are basically salty in nature. That is saline water or ocean water. That is 97.5%, and only very minute percentage of total water resources are available as freshwater resources. Among that, principal amount is in the form of glaciers. That is almost 1.725% of total global water resources is in the form of glaciers. Then so we left with only less than 1% of global water resources. If we add this 97.5 and around 2, then so 1.725, then we will be left with less than 1% of global water resources, which is freshwater resources and available to us. Among that, the percentage of groundwater is very huge. That is around 0.075%, and all other water, which is including lakes, farms, and rivers, and atmospheric water, and water which is present in the bodies of different creatures, maybe plants or animals or human beings, etc. Including all this water, that is only 0.025%, and it was even quite surprising to us to know what is the amount of river water when compared to the total freshwater resources. That is even very, very, very minute. So in other sense, if I give you the scaling of uh, what is the contribution of river water with respect to the global water resources, if we take every 1 lakh liters of global water resources, every 1 lakh liters of global water resources, 97,500 liters are in the form of oceans. 1,725 liters are in the form of glaciers, and 700 liters are in the form of groundwater. Then this, sorry, it is 0.75% approximately. It is, sorry. Then only the contribution of river water is less than 400 milliliters. That means out of every 1 lakh liters of global water resources, the contribution of river water is less than 400 milliliters. Just you imagine that how minute water resources are there in the rivers and other parts. Then, if we look into the users of these water resources, almost more than 70% of population, either directly or indirectly, are relying on the river water resources. Though the amount is very, very small, but still uh, you see, we need to look into this water resources, like uh, very minute amount, that is 400 ml. So that is why it is very important to understand that how these water resources are basically changing. So is there anything that the global water resources are changing? What the water balance equation tells us is that the total available water resources on our planet are constant. It means no a single drop of water is going away from our planetary system, nor a single drop of water is coming from the other planets. So whatever the hydrologic cycle we are talking about, which bounded between 8.5 kilometer above the Earth surface to around 1.5 kilometer below the Earth surface. So within this region, so the available water resources are constant. But what about the end users? That means population or other creatures on the planet, whether they are constant. So if we look at the one species on the planet called human being, so they are quite increasing year by year or decade by decade or day by day, we can say. So if we restrict our understanding to the Indian subcontinent, the population in the year 1951 is around 36 crore. Then now in the very recent, it is raised to 1.5 crores, almost 5 times. So within India itself, almost 4 times the population has been rise in a span of around 70 years of our independence. So just imagine that almost 4 times the population has increased, but the available water resources are not increasing. What it implies? It implies that the complex situation to the stakeholders or policymakers who basically make policies in the distribution of water resources or management of water resources. will be very, very, difficult and uh, very complex to, equally distribute these water resources to the growing population. Well, that is what where we need to, really put our focus on, and why we need to understand that how these water resources are going to change in the future under the context of climate change, or in other words, how the climate change is posing, drastic impacts on the water resources, which are very, very vital for the human survival or everything. So that and all we need to inquire. Well, let us just recall the previous things. One second. Hello, Venkat. I'm a bit busy, so can I call you after half an hour? Yeah, I have. I will send it to you. Yeah. So that is what it is there. Then, what about the availability of freshwater resources? We are polluting the available freshwater resources by means of, mixing the industrial effluents, or by using some chemical solutions to clean our utensils and all, and throwing plastic and all other waste. So these images you just see, so these are basically polluting the freshwater resources. Of course, we may ask that, sir, okay, industrial effluent that may, pollute the large water body, and if we throw plastic and all, it will also, pollute sufficiently, larger extent. But what about the shampoos and these utensils, because we use for only our household? But if you think about the, 1.5 crores, I mean, 150 crore population in our country, then just imagine that every household is releasing this much quantity of water, basically being, polluted with these chemicals and all. So this basic what happens if we emphasize or enlarge the situation to the entire world, so more and more water resources are being polluted because of our ignorance. So this is very important point where we need to put even tremendous focus. So one way the climate change has, creating tremendous impact on the available water resources, maybe in terms of rainfall patterns and all that and all we will discuss very soon. On the other hand, we from our side are also polluting the available water resources. So this is very pathetic. So that is why we need to go for, sustainable solutions. Before, 4 decades back or 5 decades back, how our ancestors used to, clean the utensils and all, so without having the shampoos and all, so how they survive for longer time. So those methods also we need to adopt in, today's scenario. Well, let us put our entire focus on what is climate change and how it impact the, water resources of a region. Uh, this is a very important topic. One second. Sorry. So basically, the climate change has manifested in terms of these parameters. One is the global temperature rise, the change in extreme precipitation events. It has manifested in terms of melting of the glaciers and rise in the sea level. Well, if we look into the global temperature rise from, last 150 years or 170 years, from 1850 to very recent past, so we can see the how the average global temperatures are rising. It has been identified that on an average, the global temperature has identified a rise of 1.2 degrees Celsius, and uh, between 1860 to 1920, the rise is, following some kind of linear trend with, very flat kind of slope. And after that, from 1920 to 1980, it has, follow some steep slope kind of thing. But after 1960 or 1980, it has started, increasing exponentially. This is no more a kind of straight line, but it is increasing exponentially. Now imagine that the global average temperature has risen by 1.2 degrees Celsius in the last 150 years. How it will have impact on the creatures or ecosystem of the planetary Earth. Just imagine with respect to our example of our body. Generally we will be very healthy if our temperature is below 100 degrees Fahrenheit. It is close to 98 or 97 degrees Fahrenheit. Will be very good mood and all. So just imagine if our body temperature rises by 1 degree Celsius, then what are the consequences? Can you imagine that you can sit in forth of this presentation and listen very comfortably? It is not at all possible. 1 degree Celsius rise of our body temperature make us very high fever and dehydration, and so many effects will be there. But the earth average temperature has rise by 1.2 degrees Celsius in a span of 150 years. Then how it has to respond, and how the other creatures on this planet are suffering. So for our human beings, we are human beings, so we can sit in the AC or something, so facilities are available. But what about the other creatures who are directly exposing to these conditions? So what kind of impact it will create on them is also equally important. In addition to that, and the main important is that how this temperature rise create impact on different important cycles like nitrogen cycle, and more specifically the hydrologic cycle. How the hydrological parameters are going to change because of this impact. So this is one of the serious evidence where we can conclude that yes, the global temperatures are rising, which is basically due to the changing climate is responsible for that. Well, we are saying that the climate is changing, but who is the responsible person or thing to this climate change? Why this climate is changing like this? What are the reasons for that? So if we talk about the industrialization and all other so-called advancements, what human being have been involved in that, so that leads to rise in the global temperatures, and eventually which is showing some adverse effects in this particular period of time. So if this adverse effects continues further, then we can imagine the very great trouble of our future generations. So how they can survive and all. So these are very important and need to put much emphasis. So what we need to what I have focused here is that if that trend is continuous, and if we are unfolding the future scenarios by means of different climate change variables, and considering the developmental activities from the socio-economic side or societal point of view, from research point of view, from different other aspects, like how the agricultural things are going to change, how the automobile industries are going to change. So considering all these parameters into account, then how the future is going to be, that has been unfolded into several ways named as climate change scenarios. So before moving to that, let us understand what is climate. Well, most of the people have some confusion with respect to the climate and weather, wherein weather is the very short-term phenomena. So how is the weather today? How is the weather before 1 hour back? How is the weather in London? How is the weather in Guntur? Or how is the weather in Chennai? So this is the right question to ask. So if your friend is going to some London, then you should not ask how is the climate in London. That is the wrong question. So your intention is to know what is the weather, today's atmospheric condition at that particular location is very our question is very focused on that. So we need to ask, this is called weather. So weather is a basically short-term phenomena, maybe minutes, hours, or days to mostly less than a month, we can say, or within a few months like that. But climate is basically a long-term phenomena. That is the average atmospheric condition or a particular location, preferably the longer period of time. So that longer period may be decade or 30 years or maybe 50 years, etc. So how it is there? Well, the World Meteorological Organization has suggested that if we are considering 30 years of average atmospheric condition at a particular location, and if we are comparing with the 30 years and how the next 30 years has changed or etc., then we can say that the climate at that particular location has no change, or else it is significant change, or the change is following a rising trend or falling trend. So whatever the conclusion we can draw, that is uh, worthful, but we need to compare with respect to quite longer period of time, that is 30 years. Then why do we need to understand the climate? Because for example, if we are able to predict how the temperatures are going to change in next 20 years or 30 years, so if we identify that after 3 decades from now, the uh, average summer temperatures are expected to rise by 1 degree Celsius over some part of India, then what it implies? The 1 degree temperature rise will create intensification in the evaporation, then it may alter the hydrologic cycle in that region, thereby the available water resources will change in that region. Sometimes more water can be possible in that location, or sometimes the water resources may decline in that same location. So these are several possible outcomes of this uh, change in temperatures. Then how the change in greenhouse gases and all will have impact on different hydrologic variables like temperature, precipitation, soil moisture, etc. These are also very important. Moreover, climate creates non-stationarity in the hydrologic time series, thereby it increases the complexity of the situation. Well, there are several studies who have put rigorous focus on understanding the climate change impacts on particularly the hydrological extremes, like what we have experienced or at least witnessed from past few days, how the situation in the northern part of our country, that is basically due to the hydrological extremes like floods. Sometimes drought is also one of the hydrological extremes. How these extremes are going to change or behave in the future period, that is also very important to address and study. Well, I hope I have given some brief introduction about the climate and all. Now I put a question in this slide that if we are aware of the future variation of precipitation or temperature in a particular region, then we can use that information for many applications. For instance, we can better manage the available water resources. We can avoid the consequences due to the hydrological extremes. Simple example, so what was happened in the last week in the northern part of our country, if we are able to model that event much prior, maybe at least 1 month before or 1 week before, then what we would have been done. So if you know that next week the northern part of country is going to be flooded, so if this information is known to you at least 7 days before, then what you will do? So we can just pass that information to all the stakeholders and the dam owners, as well as the people who are operating the reservoir and all, engineers, etc. Then they understand that yes, this particular reservoir is going to bring this much quantity of water after 1 week. So whether the situation uh, make whether we can accommodate that water at that particular point of time. or what is the situation of reservoir today. So if the reservoir is completely full, but if the event is going to be, occur in reality, then how can we manage that situation at that point of time? So it is not possible. Then what they will do, they will release some quantity of water today itself, so that they make some space for the water which is, anticipated to come in the next week. In that way, we can ensure the safety of the dam, as well as we can also ensure the safety of the downstream people. So thereby, it is a kind of cascade effect. If one system fails, then it leads to the failure of other systems towards the downstream direction and all. So, and recently you might have gone through the statement made by the Delhi Chief Minister Arvind Kejriwal. He said that unnecessarily the Haryana government is, releasing more quantity of water from some barrage that is inundating the Delhi city. So this is what will happen if we do not take the decisions at right point of time. Then we need to face the consequences. So this is very important to know how the water resources or precipitation, etc., are going to change in the future period. If we have that information prior, then we can use that information for many purposes. Of course, the example what I have given, that is basically kind of weather forecasting. But what I am going to talk here is basically climate prediction or forecasting, we can say. The general circulation models have projected the said variables up to the 21st century: the precipitation, temperature, soil moisture, wind speed, wind direction, sea level pressure, etc. So there are several atmospheric variables and hydrologic variables have been projected up to the 21st century by the general circulation models or global climate models. Then you may ask that, yes, if it is the case, so then the problem is getting solved, already solved. So why should we worry? Why we are still experiencing, this kind of hydrological extremes in the country? Well, it is because the GCMs, we need to understand about the structure of the GCM, how they have been, structures and all. So basically, they simulate the Earth's climate system over time. They describe the interaction of atmosphere, ocean, and land, etc. So what GCMs do, they basically create one more Earth in the virtual or simulation simulation world. Then they incorporate all the features which are basically happening on the earth and surface of the earth and below the surface of the earth, and how they are related by using some computational fluid dynamics and some advanced equations, etc. So everything they will Navier-Stokes equation, everything they will transfer, they will model in the simulation world by dividing earth into number of segments. So it has divided the Earth horizontal resolution of 100 to 500 kilometer, and vertical resolution, that is pressure levels in the atmosphere as well as in the ocean, of up to 35 to 25 levels. Of course, different GSMs have different resolution that will vary. So here we can see this is the entire Earth. What they are doing, they are dividing the Earth into horizontal resolution, that is 2.5 degree by 2.5 degree. That lat by long is around 2.5 degree by 2.5 degree. Majority of the GCMs. That means over an area of 62,500 square kilometer, the general circulation model is giving one value, or it is assigning one value. It is forcing you to believe that the entire Andhra Pradesh has received similar amount of rainfall in particular month. Is it true? If we are coming to the reality or ground observations, it is not true, because the rainfall will change from one location to another location. We can even expect that one end of IIT Madras there was rainfall, even it was happened yesterday. So there was rainfall at the main gate and other Velachari gate. So there is one more gate of IIT Madras. There is no rainfall. So within a distance of 2.5 to 3 kilometer or 4 kilometers, so one place there is rainfall and other place there is no rainfall, which is basically covered in the area of around 5 to 10 square kilometer, if we are considering the entire perimeter and all this region. So within this 10 square kilometer, some part is basically experienced with rainfall and some other part there is no rainfall. How can we believe that 62,500 square kilometers, sometimes the entire country will fall within that grid, having the same or similar amount of rainfall? That is quite not possible. So this is the basic limitation of the GCM, and they have not only divided horizontal resolution, but also they have divided the earth into number of vertical resolutions, that how at different pressure level, how the variables are going to change and all they have considered. Of course, to model all this thing, what I have said uh, so far is require high computational or high performing computers like supercomputers, which most of the countries are lacking, and we cannot go for supercomputers. If I want to carry out a research, so who will give me the supercomputer which worth maybe thousands and sometimes tens of thousands of crores rupees. So it is not possible to get the 10,000 crore rupees supercomputer or 1,000 crore rupees supercomputer for carrying out my research. So that is quite not possible. Then what people or researchers have done, they have developed some technique in order to bring the information from GCM from its larger scale to the finer scale. That technique they have named it as downscaling. So there are two kinds of downscaling techniques are in use. One is dynamical downscaling and other one is the statistical downscaling. In dynamical downscaling, what happens, basically the supercomputer concept will come here. So the regional climate models, instead of modeling the entire globe, they choose some part of the globe, let us say India or China or maybe Europe, etc. So they choose only some part of globe and they take the global climate model data, GCM data, and they bring that information from the larger scale to finer scale, that is RCM, at 0.25 degree by 0.25 degree gridded resolution. So from 2.5 by 2.5 degree. So, but the concept here is also same as equations used in GCM will be used in RCM also. That also requires supercomputer in order to get information from much coarser scale to the finer scale. But we can run this for only limited area. Still, it is very expensive. But still, that problem persists for common researchers. So how we can carry out the analysis using this dynamical downscaling? Well, it is not possible. Is there any technique so that we can use our normal computer and get the information for the future period? Well, that is statistical downscaling, which is being developed by the researchers, in which what they do, they take the ground observation data. You can see the right bottom figure, the ground observation data. Then they develop some relationship, statistical relationship with respect to the GCM gridded corner data, and they assume that this relationship prevail in even in the future period. Thereby, the GCM has already projected these atmospheric variables up to the 21st century, and we are developing the relationship. Then using this relationship and the variables, we can easily downscale the data for the future period. So this is what they used to do. To summarize, brief summarize the content so far I have discussed is that the impact of climate change on water resources is unequivocal, and precipitation and temperature are two vital hydroclimatic variables which influence the local hydrologic cycle most. Therefore, prior knowledge on the future variation of these variables can have many future applications as listed here. For instance, we can better manage the available water resources, we can avoid the consequences due to hydrological extremes, and the information can be useful in agricultural sector as well as urban and town planning. Well, then how to know the future variation of these variables? To answer this, the general circulation models have projected the future variation of these variables up to the 21st century. Then why we are not using the GCM data? Because the GCMs are having serious limitations as far as their spatial resolution is concerned. The coarser resolution of GCMs hinders their applicability for the local scale impact assessment studies. For instance, GCM's ability declines when the hydrological importance increases. For example, the precipitation and all other variables are very important at local scale, wherein the GCM ability it declines when this hydrological importance increases. So we need to have more importance for these variables. However, the GCM has able to predict or project the variables like wind, temperature, and air pressure, etc., even mean annual and seasonal data, etc., at different atmospheric levels, very accurate, even if we are talking about the local scale. So these variables are good, but these are not that much helpful to avoid the consequences due to the hydrological extremes, etc. Because runoff, which is basically a secondary hydrologic variable, which will be influenced by the occurrence of precipitation, frequency of precipitation, intensity of precipitation, so and duration of precipitation. All these parameters influence the surface runoff or subsurface runoff in a particular region, which is very important as far as the ground level reality is concerned. And evapotranspiration, soil moisture, these are very important variables. So these are basically dependent on the occurrence of precipitation, wherein the GCM has less well simulated when compared with the other variables, like where other variables it has been better simulated. Now what we have done, in order to overcome the limitations of this GCM, we developed some technique called downscaling. This is two. There are two kinds of downscaling techniques are there. One is dynamical downscaling, other one is the statistical downscaling. Wherein the former technique demands more sophisticated computational facilities like supercomputers, which most of the countries are lacking. On the other hand, the latter technique, that is statistical downscaling, does not require any supercomputers, but it assumes the relationship between the target variable to be downscaled and the GCM variables data is static in nature. Using this, it has projected the future variation of said hydroclimatic variables in the 21st century. However, this assumption, that statistical assumption or stationary assumption of statistical downscaling model, is a big questionable, because one way we are saying that the climate is changing, then how that relationship will be stationary, rather it is time varying or non-stationary. To address this exact point, we have developed a new downscaling model named as time varying downscaling model, which actually considers the relationship between causal and target variable as time varying rather than time invariant. So to address this, we have adopted the Bayesian dynamic linear modeling approach to successfully introduce this non-stationarity concept in this model. So the model methodology I have presented here, which starts with standardization of data, that means subtracting the mean and dividing the difference with the standard deviation. This is done for all the variables which are involved in this process. And this is the general downscaling equation, which is written as y is equal to f transpose theta plus v, where f transpose represents the general circulation models data, that is large scale data, which is not accurate. So what we are doing in this downscaling, we are developing the relationship between that large scale data and the local observation data, where theta is the relationship what we are developing between these two variables, and nu is the error term. Well, to get the where y is the target variable to be downscaled, the target variable may be rainfall or temperature or soil moisture, anything. So we will see how this model work well, etc. in very near future in next slides. So the y is the target variable to be downscaled. For our understanding, let us assume that y is precipitation to be downscaled. Then what we have done here, we need to get this theta value for the initial first time step. For the first time step, the GCM has providing the data from 1901 to 2100, Some part may be historical period, some part will be future period. So that is there. The historical period data is available up to 2005 in some GCMs, and some GCMs are it is also providing up to 2010. But well, after that, 2011 to 2100, majority of GCMs have considered it as in a future period. So now what we need to do, since the F transpose, that is GCM causal variables data, which are having great influence on the target variable, are available. Only thing is not available is the relationship. So then what we have done, this relationship has to be provided to the model by the modeler as initial parameter assumption. The initial parameter assumption can be anything except infinity. You can go for the as maximum as negative value possible to as minimum as maximum as positive value possible, including the zero. Well, so that information we have given to the model because it is quite uncertain. We don't know exactly how it relates, etc. So we can give any value. Then after giving that, so using this equation, we can easily compute what is the y value. Once y value is obtained, so we know the observed data for that corresponding time step, and now we have the downscale data. Then we can compute the error term. So using observed value and downscale value, we can compute the error term. So using this error data, we can update the posterior distribution, thereby the prior distribution. Then the model will automatically get the relationship for the second time step with respect to the information available from the first time step. So what it is doing basically, it is generating information from no information. That is the Bayesian approach. So earlier there is no information. Now it is generated some information by means of some random initial parameter assumption. That can be anything. So what will happen? This will continue the process in the similar loop, and in which what we will do, we are basically minimizing the effect of initial parameter assumption. So I identified that. So first 24 values for 24 steps. After 24 steps, irrespective of whatever the value you have assumed as initial parameter assumption, its effect is getting nullified after 24th time period or time step. It means if you assume minus 10,000 or plus 10,000 or maybe minus 50,000 or 0 or something or 0.0005 or whatsoever, the effect of this random initial parameter assumption is being nullified after the 24th.
లేదు సార్ ఇంకా
So that is basically continued in the future period. So after 24 step, every value we will get a similar kind of time series. So that we can say. Well, to get the future variation of this theta value, since the observed data is not available, what we have done, we have considered the deterministic and stochastic component of the theta values that I will explain in the next slide. So using that, we have projected the theta values in the future period, and the GCM data that F transpose is anyway available from the general circulation model from different climate change scenarios like representative concentration pathways RCP or shared socioeconomic pathway scenarios, which are very new recent scenarios. From that we can easily get that. Then we have model performance during testing and time and comparison the results. Then we can go for local scale impact assessment studies. Well, what we have done, we have projected utilized this time varying downscaling model to get the precipitation as well as temperature and other variables. Let us see the precipitation. So here blue color one is representing the observed data, orange one is TVDM downscale data, gray color is SDSM, that is its counterpart, and RCM is one of the dynamical downscaling model data. If you see this figure, more or less this graph, more or less all the models are agree good with observed mean value. However, the efficacy of TVDM lies in modeling the extreme events, where the match between the orange color, that is TVDM downscale, with respect to the blue line, that is the observational data, is very good when compared to its counterparts. So confidence is gained from the historical data. Then we have used the TVDM to project for the future period. So the theta values in the future period have been projected by considering the deterministic trend, that is trend and periodicity. So first, whatever the time series data is available, that is relationship, we have plotted here. From that, we have taken out the trend, detrended. So then whatever the second figure in this row shows, second row shows the detrended data, but which is having some stochastic or periodicity component in it. So we have later taken out that periodicity component using the second equation here given here. Then after that, whatever left is purely random in nature, and that is stochastic. So the stochastic value is being addressed using the autoregressive component one. So where the AR1 model have performed good. So in that way, we have projected the theta values in the future period. We can see that red color one is the projected theta values in the future period. So like that, we have downscaled other variables. So let us see some of the outputs of GSEMs which are published in highly reputed international journals. For instance, we have worked the work out the thing for Upper Mahanadi Basin. Then we have done the analysis for the Bhadra Basin. Then recently we have also completed the analysis for the Godavari River Basin, where in the Bhadra Upper Mahanadi Basin, it has shown some wet trend, that is, it is expected to increase by 12% in the Upper Mahanadi Basin, the annual precipitation. So where we can see that the Bhadra Upper Mahanadi Basin is going to get 12% excess rainfall in the near future or far future, as far as the worst case scenario is concerned, that is business as usual model is concerned, wherein the Bhadra basin is also shown that the stream flow events are going to intensify in near future, thereby which can have tremendous impact on the Bhadra reservoir and all. But Godavari basin, we are carrying out the analysis. The result part is over, but now we are doing the analysis, so I cannot comment how it looks. Where we have applied the model for entire India to see how the precipitation is going to change. Then we have compared the outcome with regional climate model, that is based on the dynamical downscaling technique using sophisticated high performing computers. And the bottom two rows are indicating the output of TVDM, which is basically done using the normal computer which we are using in our daily life. So you just see the outputs of the high performing computer with respect to this one. More or less, these two are matching better with the observational data, but except the Jammu Kashmir region, where the observed data itself having some discrepancies. So apart from that, everywhere we can see the better match between the TVDM downscaled as well as the RCM data, except this Jammu Kashmir region. So then we have used the data for downscaling the soil moisture. So where I have obtained the 0.5 degree gridded data as observational data, then we have seen that the difference between the observed and TVDM downscaled thing have been plotted here. So more or less, majority part is plus or minus 20 difference is there in the observed as well as the downscaled data. That is quite minimum when compared with dynamics associated with the soil moisture data and all. It implies that TVDM has captured the time varying relationship effectively when compared with other models. Well, later we have used the TVDM for downscaling the temperature over Indian metropolitan cities, and we can see the better match between the blue color and red color line in the right side portion of the figures in almost all the months and all the cities which are considered for this study. So it is true that the difference between blue color and red color line, that is observed temperature and the TVDM downscale temperature, is very minimum when compared with other models being used in this study, that is BCSD or SDSM. It implies that TVDM is basically capturing the urban temperature rise effectively when compared with other models. It is due to incorporation of time varying relationship between causal and target variable. It is very clear, and it has already published in Modeling Earth System and Environment, which is SCA journal. You can just go through that for this study. So well, later what we have done, we have differentiate the TVDM downscaled temperature with SDSM downscaled temperature, wherein the positive value indicates that TVDM has projected maximum rise and compared to the SDSM. So it is not the difference with respect to the observational data, but with reference to the difference between two models. We can see here that so overall what we can see from the right part of this images or figure, right hand side figures shows that TVDM has better match with the observational data, so we can rely more on the TVDM outputs, and TVDM has projected maximum rise when compared to the SDSM. If we put these two things together, we can conclude that the urban temperature is going to rise in the future as per TVDM outcomes are concerned, and the rise will be around on an average 1.5 degrees Celsius, from 0.8 degrees to 1.5 degrees Celsius in different regions. Well, later we have done the analysis for getting the stream flow by providing this downscale data as input to secondary, rainfall runoff model, that is HEC-HMS we have used in this study. And we can see that this is testing period, sorry, this is future period, it is written calibration, this is wrong. This is the latter part is future period from 2006 to 2035, where the x-axis is shown the correct thing. So you can see here, first part is calibration, and the next is validation, then testing, then future period. We can see that blue color one is the observed inflow data, and red color one is the inflow data by providing observed rainfall as input to rainfall runoff model. So obviously there will be very good match between the red color and blue color line, because the blue color one is basically generated as the red color line as input to that model. Of course, because of certain dynamics associated and all in the model, uncertainties and all, so the exact match is not being there, but still a very good match between blue and red color line we can see. And green color line indicates that the inflow to the Bhadra basin when the downscaled precipitation is given as input to the rainfall runoff model. However, we have got satisfactory performance as far as the calibration and validation as well as the testing period is concerned. Then we got some confidence that we can use the downscale data as input to rainfall runoff model to generate the stream flow, and future stream flow has generated, which we can see from the latter part, that is the green color part here. And this is for daily scale, and for monthly scale we can see here. So in a quick note, what I can say, conclusion. So if we can see the peaks here, that peak values in the calibration as well as the testing period. So they are having some magnitude around 200 million cubic meter. But during the future period, the peak values are quite, more in number, as well as the magnitude is also very high when compared to the historical data. That is very important, and we have seen that how many such events were there in the baseline period, and what is the magnitude of those events, and how many such events are there in the baseline period and future period, and how the magnitudes are changing. We can see from this particular table. So we have considered two events, extreme events, that is 90th percentile and 95th percentile. From this CDF plot, we can see that the value which is corresponding to 90th percentile, and on the x-axis 60 million cubic meter or something, so that we have taken out 60 or 70 million cubic meter. Values which are above 70 million cubic meter have considered. Such values are 174 in the baseline period, that is 1970 to 2000, and in future period, so sorry, 1971 to 2000, that is 30 years, and future period we have considered between 2006 to 2035, wherein the values are slightly decreasing, but the magnitude of such values are very, very high. That is, we can expect on an average 30% of what it was there during the baseline period. So 30% of excess inflow is expected to come into the Bhadra basin as far as the 90th percentile events are concerned. And the extreme most events, if you see, the events are also going to double, as well as their magnitude is also going to increase by at least 20% when compared to with the historical data. So this implies that, overall conclusion, we can say that the Bhadra basin is going to, get more than 20% of inflow values when compared with the previous year, the 1971 to 2000, in the future period, between 2006 to 2035. Well, we have submitted this outcome to the Karnataka Niravari Nigam Limited, KNNL, and they have started, taking some precautionary measures by increasing the height of Bhadra Dam, by some height and all. Well, further applications of downscaling can be, overall we can say that we can use the output for the design of hydraulic structures and operation of the reservoir, for analyzing the floods and drought events, etc. We can also use the information for groundwater management and design of drainage network. Of course, these are, very broader sense, but some of these applications demand information at much finer temporal scale, as well as much finer spatial scale than what we have done in the downscaling technique. Of course, the downscaling technique is, very generalized enough, and you can get the information for any location of your interest, but only requirement or prerequisite is that you should have the quality observational data at that location or point where you want to get the data from larger scale to the location specific. So that is only thing. But for our most of the studies, we have used IMD gridded data as input. Well, we can also put our focus on different other areas which are, very uh, uh, contemporary nowadays, that is urban flooding and all. So the urban population rise leads to this kind of situation in the urban areas and all, so which is also need to be addressed in a proper way. But for that we need to, understand, or we need to develop weather forecasting models in a effective way. Well, the downscaled output can be, very effectively utilized for the purpose of interlinking of rivers. So, well, we can see that how a basin is going to respond in the future period under the context of climate change, whether it is going to behave where it's wet or dry or something. If it is wet, then how much percentage? If it is dry, then how much percentage deficit we can expect, and what time? So, how the monsoon precipitation is going to change, how the pre-monsoon and post-monsoons are varying. So all these analysis can be done and can be used as input for, national hydrology project, very important project called interlinking of rivers. Well, we have three choices. One is mitigation. The more we mitigate, the less we need to adapt and less we need to suffer. If we are fail in mitigation, then we need to, adapt more things that will create, some kind of uh, 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 dynamics in the existing ecosystem. So will create a lot of troubles and all to the population, but still we can ensure that if we adopt more at the right time, in the right way, then we need to prepare for less suffering. And if we fail in former two, then we need to prepare for the latter, that is suffering. Thank you so much. These are some of the references. Thank you so much for your attention, and and I will be very happy to take some questions from you. Before concluding this, I would like to thank KHIT management, especially the civil engineering department and Professor Ravi Kumar Reddy, for giving me this wonderful opportunity to interact with great engineers like you. Thank you so much.
Thank you, sir. Well, it was very informative session.
Yeah.
If the participants have any doubt, if you can ask.
Just a second, I'll take
Yes.
to thank Professor Subbarao Garu from IIT Madras.
Yes,
Due to his busy schedule, still he could accept our request. Thank you, Subbarao Garu,
yeah.
for having you as a speaker in this session. Thank you.
Thank
Thank
you,
you
sir.
so much.
Thank you so much. And sorry for making some disturbance in your schedule. Yeah.
No issues at all, nothing.
Yes, sir. Yes, sir.
And happy to see you in IIT Madras, being my
Thank you so
student
much.
at Bapatla. Thank you so much. Uh, I hope you reach great heights. Thank you.
Thank you so much, sir. I am here because of you. You made very good foundation for my career. So I definitely never forget those things. Thank you so much
Thank
for everything. Yes. Yeah. Are there any questions from the participants?
Sir, feedback link has been provided in the group.
Yes. Okay.
Sir, one of our follower has been asked, can we get the data for analysis, sir?
Okay. Can we get the data for analysis? So what kind of data you are talking about? Uh, you can get the data. For example, I have presented here from two sources. One is observational data that you can get from India Meteorological Department. Let me just close this. I think. Yeah. So one is the observational data where you can get the details from India Meteorological Department, and other one is the general circulation model data sets that those are freely available, and you can get them from the coupled model intercomparison project, that is CMIP phase 6, CMIP 6. You just type in Google CMIP 6 datasets, so you can get those GCM datasets. But you need to make some registration or something. You need to provide some details so that you will get some login details there. Using that, you can easily download all the datasets. And even IMD is also providing the precipitation data, which is freely available at 0.25 degree by 0.25 degree graded scale. Even the temperature data also you can download from the same place. So yes, all these are freely available things. Coming to the time varying downscaling model that I have developed during my PhD, and now I am planning to develop some graphical user interface of that. Quite because of quite challenging things and getting time and all, I cannot ensure that when I can make it ready, but definitely I will try and take it by the end of this year if possible, so that I can also share those details with you if I can able to do that. So yes. Apart from this, you can also develop some your own downscaling techniques, and so many downscaling tools are also available. But that those are basically considering stationary assumption between the causal and target variable. Of course, that data is also useful for some of the applications as far as mean rainfall or mean water sources are concerned. But extreme events are concerned, there they made some poor performance when compared to the TVDM. So that I need to uh, tell you that you need to probably wait for some time to get this TVDM. Yes. But apart from this, everything, whatever you can use, that those are freely available. One is from IMD, one is from CMIP6, and other one is from some downscaling tools. X. Thank you. Any other?
No, sir. I think there is no doubts in the session.
Okay. Anyway, at any point of time, if you feel that you want to get some kind of thing or add something, everything, maybe comments or suggestions or any uh, clarifications, etc., you can reach me at my email ID. It is srp@iitm.ac.in. So you can reach me there. Thank you so much once again for giving me this opportunity. So if no questions are there, then can I leave?
Yeah, sir. I think there is no doubts in the session.
Yeah, thank you so much. You're Rajesh, right?
Yeah, sir. Yeah.
Yeah, thank you so much, Rajesh, for being, uh, there as some anchoring part for this session. Thank you so much, everyone.
Yeah.
Yeah,
Thank you. Thank you so much, sir.
yeah. Bye. Out. Leave it.